The operator a dagger creates a particle with momentum k. We know from quantum mechanics that such a state is not localized in space because its wave functions is a plane wave. And the interpretation of a wave function in quantum mechanics is the amplitude of probability to find the particle somewhere in space. We will recover this amplitude of probability, or at least something related to it, by acting the field itself on the vacuum. Recall that we choose the operator A in such a way that when it acts on the vacuum, it gives 0. We are interested in the amplitude of probability to find the particle somewhere. Time doesn't really matter here, so we can choose it to be 0 for simplicity. Notice that if we didn't have this square root of omega k in the denominator, we will recognize an expression for the state x. In fact, we know that omega k is just a constant in the non-relativistic limit, because that's as if the mass were going to infinity, and therefore that will be the exact interpretation of this integral. In the non-relativistic case, we will have exactly the state where the particle is found in x. However, this interpretation is not correct anymore when the particle is relativistic. Nevertheless, this is an interpretation which we use by generalization of the non-relativistic case, and we will regularly consider that the action of the field in x on the vacuum is just to create a particle in x. Also, this is strictly speaking only true for the non-relativistic case. And from that we can build a wave function. Of course, we have to be careful with this sort of notation, because here we have the state for the field itself, which is a vacuum in this case. Here we have an operator which acts on the field, and in doing so it creates disturbance of the field which correspond to one particle in x, at least in the non-relativistic limit. And that's just a number which is our amplitude of probability to find the particle in x. That's our wave function, and by coherently sum these amplitude of probabilities, we get the state for one particle. So that's a one particle state. That's a state of a field. This is how we specify the state of a particle in the framework of second quantization. Basically, this means that we replace single particle state by the action of creation operator on the vacuum. And similarly for a particle in x, we can generalize that to any single particle quantum state belonging to the Hilbert space of one particles.